In 2021, humanity will see 13 billion years into the past, and a time machine has nothing to do with it. One of the most expensive projects in the history of space exploration, the James Webb Space Telescope, or JWST, or just Webb, will help us see the universe as it was shortly after the Big Bang. Compared to its predecessor, Old Man Hubble, the Hubble Space Telescope, it is what a digital microscope is to a magnifying glass. So, what amazing secrets will we discover with it? And how might our ideas about the world radically change? This project is by no means a brainchild of just the past few years. For the past quarter century, it's been nursed to life by experts from NASA, Canada, and Europe. It was named after the second head of NASA, James Webb. James Webb headed the Office of Space Affairs from 1961 to 1968 and supervised the United States' first manned launches into space. The new telescope was first planned for launch into orbit in 2007, but has since been delayed more than once. Now it's been scheduled for late March 2021. On that date, James Webb will join the Hubble to perform tasks including the creation of a 3D model of our universe. After 2030, the Hubble will go on a well-deserved rest. Since its launch in 1990, it's provided more than 1 million images of thousands of stars, nebulae, planets, and galaxies. Of these is the picture of the UDF-J-39546284 galaxy, located 13.4 billion light-years from Earth. That is, the Hubble captured images of stars that shone about 380 million years after the Big Bang, which supposedly happened 13.7 billion years ago. While these objects may no longer exist, we still see their light. Some of the Hubble's images include stars up to 10 light-years away from us, which we observe in their exact form from 10 years ago. Now, we expect James Webb to show us the universe as it was only 100 to 250 million years after its birth. This will not only help scientists understand the processes that took place at that time, but perhaps also transform our current understanding of the structure of the universe. Additionally, the James Webb will be able to observe planets and their satellites found outside of our solar system and learn a lot about Earth-like exoplanets. For example, we'll be able to determine their density and analyze the composition of their atmospheres in order to understand what type of object the planet is and whether there's life on it. The Spitzer Space Telescope, or SST, and Hubble telescopes have collected data on the gas shells of about 100 planets. According to experts, the James Webb is capable of exploring the atmospheres of more than 300 different exoplanets. So, how does it work? The James Webb is an orbiting infrared observatory that will investigate the thermal radiation of space objects. Remember, all solids and liquids, when heated to a certain temperature, emit energy in the infrared spectrum. Here, there's a relationship between wavelength and temperature. The higher the temperature, the shorter the wavelength, and the higher the radiation intensity. James Webb's sensitive equipment will be able to study cold exoplanets with surface temperatures of up to 27 degrees Celsius or 80.6 Fahrenheit, a drastic difference compared to the average surface temperature of our planet, 15 degrees Celsius or 59 degrees Fahrenheit. An important quality of this new telescope is that it will revolve around the Sun and not the Earth, unlike the Hubble, which is located at an altitude of about 570 kilometers or 354 miles in low Earth orbit. With the James Webb orbiting the Sun, it will be impossible for the Earth to interfere with it. However, the James Webb will move in sync with the Earth to maintain strong communication. Yet the distance from the James Webb to the Earth will be between about 374,000 to 1.5 million kilometers, or between 232,400 and 932,000 miles in the direction opposite of the sun, so the potential for breakdowns needed to be eliminated. In other words, the distance from the Earth to the telescope will be almost 4 times the distance of the Earth to the Moon, and as such, its design must be extremely reliable. However, in this case, reliable does not mean heavy. The new telescope weighs 6.2 tons compared to the Hubble's 11 tons. Nonetheless, the James Webb exceeds its predecessor in size. Its length is that of a tennis court with a height of a 3-story house, while the Hubble is no larger than a bus. The first piece worth noting is the main mirror of the telescope, with a diameter of 6.5 meters or 21.3 feet and a collecting area of 25 square meters. That's 269 square feet. It resembles a giant honeycomb consisting of 18 sections. On the Hubble, the diameter of the main mirror is 2.4 meters or 7.87 feet, almost 3 times smaller in size, with an approximately 7 times smaller surface area. Due to its impressive size, the main mirror has to be folded for startup. This giant size will capture light from the most distant galaxies. The mirror can create a clear picture and eliminate distortion. The first segment of the mirror was installed on the telescope only at the end of 2015 and wasn't completely assembled until February of 2016. A special type of beryllium was used, which retains its shape at low cryogenic temperatures. The front of the mirror is covered with a layer of 48.25 grams or 1.7 ounces of gold, 100 nanometers thick. Such a coating best reflects infrared radiation. A small secondary mirror, called the secondary, opposite the main mirror, receives light from the main mirror and directs it to instruments at the rear of the telescope. To improve quality, 2 more curved mirrors collect the image from the surface of the main mirror. Yet, the biggest element of the telescope is not the mirror, but the sun shield. Resembling an enormous pie with a length of 20 meters or 65.6 feet and a width of 7 meters or 23 feet, it's composed of 5 very thin layers of Kapton polyimide film. This protects the mirror and tools from sunlight and cools the telescope's ultra-sensitive matrices to minus 220 Celsius or minus 364 Fahrenheit. Otherwise, the infrared glow of the telescope parts would interfere with the clarity of observation. The shield should quickly, within 2 weeks, and smoothly expand and collapse. Thanks to its amazing thermal insulation, you could fry pancakes on one side while water instantly freezes on the other. The third main part of the telescope is the central computer, which controls the operations of the observatory while in orbit. Still, more scientific instruments will be helping the telescope in its operations. Firstly, the NIRCam, near-infrared camera, is actually the main set of eyes of the telescope. With the NIRCam, we expect to be able to view the oldest stars in the universe and the planets around them, as well as create a map of dark matter. Secondly, the NIRSpec near-infrared spectrograph will collect information on both the physical and chemical properties of an object. Next, the MIRI mid-infrared instrument will allow you to see stars being born, many unknown objects of the Kuiper Belt, and, as astronomers hope, will help in the search for the mysterious 9th planet of the solar system. Fourth, the Near-Infrared Imager and Slitless Spectrograph, or NIRISS camera, is aimed at finding exoplanets and the first light of distant objects. Finally, the FGS, or Fine Guidance Sensor Precision Pointing Sensor, helps accurately point the telescope for higher quality images, updates its position in space 16 times per second, and controls the operation of the steering and main mirrors. They're planning to launch the James Webb with the help of the European launch vehicle Ariane 5 from the Kourou Cosmodrome in French Guiana at the Guiana Space Center. If everything goes well, $10 billion worth of construction and a half year of preparation will have finally started in orbit. The device is designed for between 5 to 10 years of operation, but may serve longer. One may ask, why not keep the James Webb on Earth? Why do we need it in space? The fact is that water vapor and other elements in the Earth's atmosphere absorb most of the cosmic radiation, which interferes with ground-based telescopes. The situation is further complicated by clouds in the Earth's atmosphere and noise and vibration on the Earth's surface. None of these issues affect a telescope in space. As such, it can achieve a resolution many times higher than that of a telescope on Earth. So, with the help of the James Webb, what secrets of the universe would you like to explore? If you liked the video, thumbs up, subscribe to the channel, click on the bell to be notified of new videos, and don't forget to recommend us to your friends.